Hello everyone, welcome back to Exam Prep Tool. So this is going to be one of our last revision session for before Gate D exam. And within this particular lecture, we'll be talking about ML short notes, which will be helping you in revising your machine learning as fast as possible. Okay, so make sure you remember everything. So you just need to just uh, check mark everything what is being followed in our ML short notes, and then it would help you increase your confidence with respect to exam, that yes, you are aware of most of the important topics, and you must be having your own checklist as well with respect to what you are forgetting, what you are able to recall. So make sure you revise that as well, but this is overall idea, like the general ML short notes kind of a thing. Okay, so let's get started. uh, yeah, so this very rarely will be writing anything within this particular lecture, as it is going to be mostly about what exactly already lies there, which you have studied, you have already solved problem, but it is just more about what exactly lies like I said already. Okay, so we'll start with when we start the subject, it generally starts with what exactly is machine learning. Okay, so we will not just waste time over there, like very typical what definitions over there, but something which actually comes handy. So machine learning is nothing but learning from the data. Okay, now when I talk about learning from data, it means that we are some kind of trying to recognize patterns, or if I can just make sense of data, if I can use that data to learn something out of it. Maybe slowly, as I keep getting more and more data, I would learn more. So within this, the words or the statements I used, I actually tried to justify it, all the approaches we are having, majorly like supervised learning. So we are learning, we are trying to recognize some patterns given some what should I say, giving some supervised idea. That means, do we know that okay, the images of cats looks like this, images of dogs looks like this, the rates of houses in this area are like this. So we have that supervision apart from the data we are having around them. Okay, the other part which I said was unsupervised learning. So we just try to make sense out of that. Okay, within data, is there some clusters, are there some similar looking data points, something like that. Okay, on a higher level. And then the other word, the last one which I talked about, was something like when we try out interaction with environment, we keep getting more and more data from the environment, and then we keep learning, kind of reinforcement learning. Okay, so now we'll get into the supervised learning idea, and then the algorithms which exist within that. So we have the labeled data. So X is generally though this is just a tuple given over here, but Xi need not be just one value. Xi can be a vector, which would be something like I'm having a feature space I'm talking about. For an example, if I'm saying that I would like to predict, let's suppose, yeah, would there be, like, what would be the rate of houses. So I'll consider is there is the flat or the residential area you are talking about, to predict its price, is closer to some big park, is it closer to some, is it connected via highway or maybe metro station or maybe the airport. Okay, how far these things are, and something like in that area itself, what exactly is the what should I say, how is the water supply and all. Okay, apart from that, the number of rooms within this particular house. So all these things can become feature for my first data point, and why I would be, what exactly is its rate. And that's how we will try to learn from this, like n data points, and then after learning, we try to predict for some unseen data, that what, like, did I really learn something or not. It's like you have learned machine learning. Now if you'll be given some questions which you have not seen, but you have understood the concept intrinsic to it, if you have learned, you shall be able to answer. So something like this only. Okay, so the goal is always to understand the mapping from x to y, that what exactly is that function which actually helps or basically translate features into my final output, which is generally the label. If it's a continuous value, in that case, what I'm doing is I'm actually doing a regression. If it's a discrete or categorical value, in that case it's a classification. And in general, in supervised learning, what we study at this level is that they generally, the training and test data are drawn from the same distribution. Okay, we have a number of variations if you go higher for the studies, nothing relevant right now. And we consider IID samples. Okay, what do we mean by IID? Independent and identically distributed samples. Okay, cool. Let's move ahead. So yeah, regression versus classification. You already have that idea. In one, we are actually predicting a number, and the other, we are actually predicting a kind of a class. Okay, uh, and there we have accordingly the loss functions, and the example is also given. So if I talk about loss function, it's going to be mean squared error or mean absolute error. If I talk about classification, in that case, the log loss, nothing but our what should I say, the entropy loss, and hinge loss, which we generally see in SVM. So there are other losses as well, but right now just justify. We have these example like price prediction, and classification would be example would be spam detection. So if an email is being sent to you, there is always a spam detection running within your Gmail, which actually try to classify whether an email which you have received is a spam or not, and according to that only it pushes the one it into pushes it into your spam folder. Okay, so the idea goes like this. Okay, so yeah, let's move ahead. So now it's turn for the algorithms. So the first algorithm is simple linear regression. So see, this is just an introductory part in which we generally study that there is only one feature based on which we are actually try to predict the output, and that's what we call a simple linear regression. Okay, but overall linear regression idea is that we have a number of features and we are trying to fit a line by in order to predict the y variable. That's the general idea. So we have the features, we try to find out what should be the line which can actually model my data. So that's the idea. So if I'm talking about just simple linear regression, in that case I'm just having one feature. Okay, x over here, this is intercept, and this is the irreducible noise kind of a thing. Okay, so or a random error. So this is how our overall model looks like. The objective would always be to minimize your mean squared error. How do we write mean squared error? So first of all, you need to find out the error. So for that, y minus y cap, and then take square of that, sum the error for all the data points, and then take the mean. That's your mean squared error. And then you try to learn the parameter beta naught and beta 1. That's what we try to learn. Okay, now like a simple, so we are not going to do any kind of derivation, but we do have formulas directly. So how do we actually find out? There is a closed form solution for that. Beta 1 would be equal to summation of xi minus x bar, that means the mean of x, yi minus y bar, that means mean of y, and the product of that getting subbed up. So for each of the value, if I had something like, let's suppose in x we have 2 3 4, and in y we had 1 2 or something like that. So you calculate the mean first of x, calculate the mean of y, subtract from their corresponding row value, you get xi minus x bar, you get yi minus y bar, and then what you need to just do is you need to take the product and sum it all. That's how you'll be getting your first, or basically the numerator. To get the denominator, it's more like something similar to how we calculate our variance. Okay, or it could have been simply calculating the mean of this particular stuff, xi minus x bar into yi minus y bar, because you're already having summation, you just need to divide by n. For this also, if you divide by n, so it's like a common thing. If you have that mean, you just need to divide those things, but just an extra step, it's just telling you. So summation of product of these and summation of square of the xi, basically the deviation, uh, and then that's how you get it, the your beta 1. What would be beta naught? So you already know it is going to be simply y bar minus beta 1 x bar. Okay. So what is the key properties? So these are like unbiased estimators. It is very sensitive to outliers, and because if there is an outlier, in that case your line itself might shift a lot. Okay. And it assumes linear relationship. Okay. So the word linear regression, the linear itself, it is telling us that we are going to have linear relationship. But does that mean that with linear regression we always try to create, what should I say, or basically the kind of idea which we use would always be linear? It depends upon the kind of feature we also create. If I am creating some advanced feature and then try to fit a linear line, it may be something that my true data was lying in two dimension, and then I created something high dimensional, which became like, what should I say, like the way I actually transition from smaller dimension to higher dimension can be a complex function, but in higher dimension also it still remains like it seems to be just a linear regression. So over there we can have this kind of a, what should I say, mismatch thing, that we are actually doing linear regression, we were doing it, but we actually use some non-linear transformation earlier. Possibly, it's always possible, okay, and still fitting the linear regression line. So that's kind of thing which are always possible. But overall idea is linear regression. In linear regression, we are always trying to fit a line most of the times. Okay. The next thing is multiple linear regression, in which we have a number of features out there. What would be the matrix form looking like? Y equals x beta. And if you write W1, W2, something like that, it would be XW plus epsilon. The normal equation, that means the solution, if you would like to find out, is the overall beta vector would be x transpose x inverse into x transpose y. That is going to be a solution, normal equation solution, closed form solution. Okay. So yeah, that was the idea. One important, very important thing. What are the assumptions? So this is very important. So you can always remember this keyword or kind of statement, line rule. Okay, what does this tells? It actually considers all the assumptions which are part of linear regression. Okay, I'll talk about something very important as well over here. First, let's finish these assumptions. So the first assumption is linearity, that there exists a linear relationship between your data and y, basically the features and y. Okay, it has to be true. But sometimes what happens is your data itself is not linear. Okay, you might have some curvy kind of a data, possible. Okay, or kind of a wavy kind of a data is also possible. So in that case the data itself is not linear. So that's where I talked about that we might actually project our data into higher space, or we might transform our features in such a way that after projection or after transformation the data then looks like linear, because ultimately I should be able to bring the linear relationship. If I'm able to bring it up, then linear regression will do amazing job in predicting. Okay. So the first most prior assumption is the relationship has to be linear. After that, independence. Residuals are independent. That means whatever error I'm getting from, let's suppose the first data point should not be anyhow related to the error I will be getting for fifth point or maybe 10th point or seventh point. Each of these must be independent of each other. Residuals are independent. Okay. Normality, what does normality means? So whatever error I'm getting, that should follow a normal distribution. That means most of the time the error should be around zero, is what we generally want it to be. Okay. And there can be some here and there. That means on either side, like if I'm projecting a simple line or giving you a simple line as a like linear regression model, as I go far from the line, I shall be getting less number of actual data points. That means overall error should decrease when I go far from the line. Okay. The overall number of points I'm talking about. Okay. Because the error also would increase. So it's like Is it possible to get like a error of, let's suppose, 100? It's possible, but the possibility of that should be very less, okay, on either side. So that's how we are saying the normal distribution, because most of the time the error should be around zero only, so it should follow a normal distribution there. Equal variance, very important. Homoscedasticity, what does it mean? That overall my variance should not depend upon the scale of features, okay. So if I'm increasing, like for an example, if my x1, x2, like these were the features, as they are increasing, the overall variance in my what should I say, in my residual should not increase. That I am getting more and more variation. For an example, I started from here, that overall error was less, but as I'm going further, it's increasing, and in middle there exists the my linear regression model line, okay. So it shouldn't be that if I'm increasing the x, the overall distribution of my error is increasing. No, it should be, it should remain constant, okay. That's how we will be able to say that, yeah, the linear regression would hold true. If any of these assumption actually fails, the linear regression model would not really work in that case, okay. There is fifth point as well, which people generally talk about, but let me be honest, that's not really an assumption, and that point is multicollinearity. So multicollinearity is nothing but if there exists some correlation between the features itself, okay. So in that case, your linear regression would still perform, okay. There would not be an issue. It's just that the problem would be with respect to understanding the feature importance, understanding the feature importance, interpretability, something like this. Because somehow when you model it this way, you know, if beta 1 value is going to be higher, in that case you are saying that, okay, contribution because of first feature is more. If beta 2 is very less, you'll say that x2 contributes very less, okay. Now for that kind of an idea, to understand the interpretation or, you know, feature importance, you need to just think about one important thing over here. What is that? That, okay, if there these features were independent from each other, in that case it would make more sense to interpret like this, the way I said, one is contributing less, one is contributing more. But if there had been some interleaving, for an example, let's suppose your x3 feature is nothing but x1 plus 4 times of x2 only. X3 value is nothing but x1 plus 4 times of x2. In that case, what would happen is, it's not an independent feature you are having. It was something correlated with existing feature. So now you'll not be able to interpret it properly, because x4 x3 contains some component of x2 and some component of x1, okay. So the problem of multicollinearity, or the assumption of multicollinearity, does not really strong like hold strongly for the linear regression. Like even if it there exists multicollinearity, it doesn't really matter, or it doesn't give a problem to linear regression. It only problems create problems in case of when we want to interpret the features, or we want to provide the feature importance. Only in that case we actually talk about this thing. I hope we are clear. Okay, so linear regression assumptions are clear. Let's move on to the next one. So then we have the ridge regression, L2 regularization. So ridge regression is nothing but, as I mentioned, so we had the linear relationship. It may be the case that the data we got from the for the training purpose might, like it, overall data is linear. We are assuming that only, but the points were in such a way such that I was getting this kind of a line, but the complete picture was unknown, where we get to know that the line has to be a little more tilted. Okay, it's possible when we get more data points, a tilted line, a little more tilt might make more sense to me if I get more data. But the thing is, we do not really expose all the data while training, because we want to generalize better. So what do we do in that case? We actually let go of some of the accuracy of my training accuracy. We'll just let it go, and that's what we call as bias over there as well, which we'll talk about in bias variance. So in rich regression also we are doing regression only, but there is an important component to the cost function, which is nothing but summation of square of weights. Okay, beta were the weight value, so we actually sum those up over here, and then that's how we actually add it to the cost function itself. Now if weight values are too much also, my model would try to decrease beta values as well. It would not try to keep it as high as possible. Okay, so that's our L2 regularization or ridge regression. Okay, so okay. Now the next thing would be what, like, does there any kind of closed form exist? Yes. So we have a solution there as well. X transpose X plus lambda I. So you can see the lambda I is the component which gets added as compared to your multiple linear regression. Okay. So this is the only part because lambda is being added over here as part of your what should I say, regularization over here. Okay. So as your lambda increases, always remember you're giving more weightage to this component. And if you give more weightage to this component, it would focus less on this and would try to focus more on this, decreasing the beta values. If lambda is less, let's suppose if it's 0.001, it's similar to saying that I was only focusing on this rather than this. So you can see how lambda value can, shift the focus from the main error to the weights of sorry, to the like the scale of weight what we wanted to learn. Okay, depending upon that. So if I increase lambda a lot, in that case my overall linear regression model would try to decrease beta values. Okay, the scale of beta values. Cool. So closed form we have. So in this case, what happens is the coefficients are like they are scaled down. So they are shifted towards zero. They never makes coefficients exactly zero. Remember, they would decrease it. They would never make it zero. We have a different regularization which is coming up next, which actually make it zero as well. Okay. So while doing regularization, what happens is we sacrifice some accuracy in order to generalize better, and that's how our bias would increase but overall variance would decrease. Okay, because that might help in general for my overall data. Okay, for my overall test data. Let's go next. Lasso regression, which is nothing but L1 regularization. So here also we have the same kind of thing. It's just that right now the weight contribution for my error calculation or for my loss function would be that I'll be adding modulus. That means I would like to add magnitude only, not the signs, magnitude of my weights. Okay, and again we have lambda over here. So lambda would do the same work over here. If I increase the lambda, we would like to decrease the beta more. If my lambda is less, I would focus less on decreasing, though I will be decreasing, but would focus less on decreasing, but would focus more on this. Okay, so that's a regularization parameter we are having. uh, how do we optimize? So see, the previous one, this was a simple, yeah, like classic what should I say, convex function type of thing we are having over here. But this is not differentiable. The modulus function are not differentiable. So how do we actually solve this up? So there are different methods. So like but what we generally use is the gradient descent method. Okay, so that's what is being used to solve this problem and to find out what should be the weights overall. Okay, what is the difference between ridge versus lasso? You should remember this particular table. It will help you a lot with respect to regularization. Ridge is a L2 regularization, lasso is L1 regularization. Can one of these be used for feature selection? Yes, lasso can be used for feature selection because it just does not decrease the betas. It actually put them to zero as well. Okay, so because it puts down to zero, that means it is eliminating the contribution of some of the features. So inherently it is trying to tell me that this feature does not matter. So kind of feature selection it can provide if you want to make some complex modeling. In that case, over here, lasso regression can be one of a simple technique for the feature selection. Coefficients, what happens with the coefficients in each one of these? So they become smaller but non-zero for ridge, but in lasso they can exactly become zero. Do we have a closed form solution for both? For ridge we do have, that like you could see plus lambda I and then this similar kind of a thing. But for a lasso we do not have. For lasso we have to go by the gradient descent kind of method. Okay, so that was all with respect to the regression, more around the linear regression. Okay, so the next thing which we get is the logistic regression. So the model says classification problem. You already know we have the features, we want to predict something. So right now we are saying we have the labels 1 or 0. Okay, and with that only we would like to predict what would be like what is going to be the probability for this, and depending upon the probability we would like to assign the class. So for an example, in general, what do we say? If the probability is greater than zero point 0.5, I would say that the class was 1. If it is less than zero point 0.5, in that case I would say 0. But it matters. Okay, it's not always that a zero point 0.5 is a fixed probability threshold value we are going to take. Sometimes it can be 0.7, sometimes it can be 0.8 as well, depending upon the scenarios. Okay, so the general idea is how do we actually determine this thing? So the idea is we have our features, then the same kind of thing happens actually, that we actually try to what should I say, uh, we try to get some linear output by using some linear relation of the features, and then we try taking what logistic function of that, like we try to use this function to output probability from there. Because if you just see what exactly is the range of this function, it would be from 0 to 1. Because you can see if z is infinity or minus infinity, what do you get overall? You can just get this idea. And z overall is nothing but a linear function of your features itself only. Okay, and how do we actually determine this? Like this, you can see directly. The other way to look at it is uh, the log of odds of a particular class is equal to nothing but your linear relationship in terms of x. So what do I mean by that is, you can also write like this log of odds, like how will I write it? We finally got something to write over here now. uh, Log of p upon 1 minus p is equal to beta, or basically like what we generally write, w transpose x. Now when I'm saying p is basically, I'm just talking about for class label 1 only. So if you just solve it up, what you will be getting is nothing but this one only. That means p would be given as 1 on 1 plus e to the power w transpose x. You'll get this only. Okay, so this is another way that, okay, the log of, or like the log of odds should be equal to your linear projection of your features. Decision rule we just talked about. What is the log function which is being used? Binary cross entropy loss. Okay, where y cap you get from your model, y you already know that is it class 1 or class 0, we always have. Okay, so that's how we get this loss function. How do we optimize this? So in general we do not really have like we do not have the closed form solution. That means direct equation based solution we do not have. We use the gradient descent to solve it up. What is going to be my decision boundary? The w transpose x or beta transpose x equals 0. So it is always linear in the feature space. Okay, but non-linear if features are transformed. So like after we transform, it can be non-linear as well, as I talked about the linear regression. So that was all about the regression kind of thing. The other models which we are going to talk about can also be used for regression, but the way we study generally is in context of classification. Okay. So next is our k nearest neighbor. What is the idea? So like the overall thing is it. So the same thing. The similar looking data points would always be in closed proximity of each other. That's the idea. What is the overall, what should I say, like the points you can remember around it is instance based, it is a lazy learner, and it classify based on the majority vote among the k nearest points. So k nearest neighbor suggests if there are 5 nearest neighbors, what is the what should I say, dominating class over there. Whichever is the dominating class, that is going to be the class of this test point I'm having. Okay, if I don't know about the class of that. Now, for that to determine the similarity, or what should I say, I'm saying that okay, this actually matches a lot with this particular one. How do I determine that similarity? So it's just nothing but we use distance metric. Similarity is nothing but inversely proportional to distance. More the similarity, lesser would be the distance. So closer a data point is to my test data points, I would say it is more similar. So as the moment comes when we talk about distance, so in general we use two distance metrics: Euclidean, which is you already know about, like L2 distance. It had been something we had been doing in our school time as well, a simple coordinate geometry based distance. Okay, Manhattan distance is much more like the absolute distance is we are having. So over there we do not really jump from one point to directly to other, but we actually look in terms of how many unit steps horizontally or vertically we need to take, or basically in each of the axes or dimensions we are having we need to take, rather than jumping directly from point to point. Okay, so that's Manhattan distance. So like you must be having that story around Manhattan and all, but overall idea is Manhattan distance would be the summation of absolute uh, uh, absolute differences between your end and goal with respect to each of the dimension. Okay, so if I'm at 1 1 and 5 5, I'm talking about Euclidean distance would be 5 minus 1 square plus 5 minus 1 square root of that, because 1 1 to 5 5 I was talking about. But Manhattan would be 5 minus 1 modulus plus 5 1 minus 1 modulus. Okay, so both would give different value, but is giving me the distance. Now feature scaling is very mandatory in k nearest neighbor. See, and this is what I would like to say is general for all those algorithms which uses some kind of distance metric. So if you are using the distance metric, in that case scale matters a lot. If one feature is having a scale in, let's suppose, thousands, one is having the scale in, let's suppose, unit digits only, then the one which was having in thousands would dominate. Okay, so what we want to do is we do not really want any feature to get to take any advantage to decide what should be the class. In that case, the feature scaling is required. We use min-max scaler, or we use standard scaler. Okay, where we just try to normalize by taking the by subtracting the mean and then dividing by the standard deviation. It's a standard practice. Otherwise, in distance based algorithms, it is going to suffer a lot uh, because of the outliers and all. Okay, so feature scaling becomes very important over here. So yeah, choice of k. If the k is small, will be having low bias but high variance. If it's small, in that case, I might be just looking at the very nearest neighbor only. For an example, k equals 1, but it might give me high variance, because if I do not know about the overall data, I might suffer. I may not be able to predict properly. If my k value is large, in that case I'm getting true sense of what exactly lies in my overall uh, area. So if I see from the perspective of generalization, I know I would be having lesser error. But if I talk about the lesser data points present right now, I might be getting more error than the k was 1 only. So complexity, we'll be talking about complexity. We have a slide for that. Soon we'll talk about that. So pros, cons, or general features about it is non-parametric, as we do not really have any kind of assumption with respect to like how should the data look like in KNN. It suffers from curse of dimensionality, because we are actually getting into each of dimension to know the difference. We're going to square and then sum it up, take the root if it's L2 distance, or directly just sum it up if it's Manhattan. So if number of features are more, in that case we are having trouble for it. And it's basically true for all the distance based algorithms. Okay, high test time cost, because there is no training at all. It's only testing. At testing time we do all the stuff. So it has like high test time, and k should ideally be an odd number to avoid ties. So if you're just looking at four nearest neighbor, and in that case if you get two positive, two negative, what would you do? So we do not want those kind of ties. In that case, we take it to be an odd number, 357, because we know in that case we will never be having ties, and of one of the class would always be majority or the dominating one, according to which we would like to assign the label for new test item or new test data point which we are having. Okay, let's move to the naive Bayes. So it's a generative model based on Bayes theorem with the naive assumption. What is that naive assumption? That features are independent conditionally. And what is that condition? Conditioned on your class. So feature are conditionally independent given the class label. Okay, that's how we generally talk about this. So the moment we say the features are independent, conditioned on the class, we can write them individually as a product of all. So p of xi given c p of x2, like if we had five feature, p of x1 given c into p of x2 into p of x3, something like this for all given c. That's how we generally write it. I know, I'm still like you have studied it all, but just trying to help you recall that this naive assumption is a very powerful assumption, though it does not really hold true always in real world, but it still works. It's just saying that okay, it should be conditionally independent. It may not be true, but it still works and give very good results as well. Okay, but why do we actually bring the idea of naive assumption? Is a simple reason for that is to make our calculations easier. Okay, because otherwise if we have too many features it would be difficult to model in that case. Now there is one thing which we generally study, which is Laplace smoothing. Why do we have Laplace smoothing done? So like you'll be always calculating something like this. Okay, now the moment you want to calculate something like this, it's possible that this probability itself is zero. Now just consider you would be soon multiplying a number of probabilities. Like over here you'll be multiplying a number of probabilities, and then the prior, what is the probability of getting this class, you'll be multiplying them, and that would give you the posterior or the idea that what should be the class. When you'll be doing it, if p of x given y, that means because of any feature if it's zero, the overall it would become zero. We don't want that. Just because of one feature which is having zero probability, it would make the entire multiplication to be zero. Doesn't make sense. So we need to add some smoothing so that we get a very small value if possible, but it shouldn't be zero at all. Okay, so there we do some kind of smoothing where we add alpha value. Okay, so the example is being taken from the simple NLP idea, or you can say the spam classifier kind of an idea, where alpha is generally chosen to be 1. That means while calculating this probability, always in numerator will have 1 divided by what do we have? What we will be adding extra? The vocabulary size. What is the overall number of words we are having while trying to classify a mail as a spam? Okay, so we do something like this over all so that we can actually what we can actually avoid the idea of getting a probability of zero. Okay, and then this overall helps. So one more thing, we never calculate p of x. That's the evidence, because if my like class label is 1 or 0, this is not really contributing in telling that which class it should belong to. It can help me in calculation if I want exact answer, but if I just want majority class, like p of x would be common to both. When y is equal to 1, y is equal to 1, y is equal to 0, y is equal to 0. So I don't want px to be calculated. So in that case we say p of y given x would be proportional to the multiplication of numerator only. So we calculate the numerators only. Whichever value is higher, that is going to be the class getting assigned to the test point. Okay, because p of x is always same for every class, the evidence. Okay, we don't want that. We just look for the scale wherever the product of likelihood and prior is more, we assign that particular class. It is very fast. It works with the small data, especially it does amazing work on the small data. What are the different types of naive Bayes? Gaussian naive Bayes, multinomial naive Bayes, Bernoulli naive Bayes. Gaussian if the features are continuous, multinomial if we have discrete counts, okay, a number of counts exist, Bernoulli if it's just binary features we are having, okay, something is present or not, something like that. So that was our naive base. Now we'll move on to the LDA, linear discriminant analysis. So idea is it is a kind of dimensionality reduction technique, but supervised, because we are again looking for a projection such that I am decreasing the overall, what should I say, my like I'm bringing it down to the lower space by projecting onto some space. But the idea is while projecting, so I would like to increase the separability of two class. That means if we had the data points from two different classes, I want such a projection such that it would increase the overall distance between these two, okay, and should decrease the internal, what should I say, the within class variation should also be considered for that. So I would like to maximize that and minimize what should be the internal to every cluster, or to every class, whatever is the variance, want to decrease that as well. And that's how we get the objective function of LDA as well. So the idea is we want to maximize this ratio between class variance, that I would like to increase so that they are far from each other, but I would like to decrease the within class ratio, within class variance. That means within the class the data point should not be having much variance, because if it's too much, the classes might be overlapping. I would like to decrease them, okay. So that's the idea. So while projecting, we have to like bring it up such that we get this kind of an expression overall when we are actually looking for the objective function or the cost function. And the moment you try to optimize it, you get the plane or the hyperplane or the projection plane, which actually does the work which we were talking about. So what are the assumptions? The data in each class is normally distributed and all classes share the same covariance matrix. That means within each of the dimension, both the class have the same variance. That has been already assumed. So that's a linear discriminant analysis assumption. If it's not, then we have to go to the QDA kind of a thing, quadratic discriminant analysis. Okay, so always remember the assumption as well. Now, how it is different from PCA? PCA is unsupervised. We do not really have class labels to actually reduce the dimension. Over here, we had the class labels which actually guide me that how I should decrease my dimension so that I can increase the separability. Okay, so PCA is unsupervised, looks for maximum variance, whereas LDA is supervised, looks for maximum class separation. Both have different meaning. And I hope you have, I still remember we have solved that question, which actually helps us in understanding this part. Okay, that was all in LDA. Now we get to the SVM, support vector machines. So SVM finds, so what actually happens is in SVM, there is something called support vector. And what is that? We have that idea, but need not worry. First of all, the idea is we would like to find out the margin such that margin is nothing but a kind of, what should I say, uh, it's a distance between the two classes we are having. Distance, and how do I determine that distance? Because if I talk about data points here, data points here belonging to different classes, I'm not actually talking about, okay, what is the distance of this point from this. That is not my margin right now. We calculate a kind of a margin, a distance metric, which we always want to maximize, which provides the separation between these two classes. And that's what we call as margin. How do we find out is we actually try to find out two lines. If it's in two dimension, if it's in high dimension, we will talk about hyperplane, two hyperplane, which actually helps us in separating these two classes. And while doing so, I would like to keep them as far as possible. So this is kind of a, what should I say, a gatekeeper for all the data points belonging to this class. This particular was a gatekeeper for all these data points. Now what I want is, I want these two gates to be as far from each other, and the distance between these two gates is called as margin. And that's the idea, that we want such hyperplanes to be calculated such that I would like to maximize this distance. uh, and what would be my final decision boundary? A line or a hyperplane just in between these two. In between these two would become my final hyperplane. And that's how we give it, like same like hyperplane equation. W transpose x plus p equals 0. So the margin is the distance between two hyperplane and the closest data points, which are called support vectors. Support vectors are nothing but with the help of which we actually create our what should I say? Uh, 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 those hyperplanes which were actually, uh, yeah, sorry, these hyperplanes which we were actually calculating. So the distance between these two is nothing but margin, and support vectors are those data points which either. So if I just talk about the hard SVM, then in that case, support vectors are nothing but those data points which lie on these hyperplanes which we just talked about. Okay. So there is margin width, which we always want to maximize 2 by uh, L2 norm of W. Uh, and the opposite of this can be said as that we would like to minimize half of my L2 norm square. Okay. Now hard versus soft margin. Now within hard margin, what we actually prefer is that there will not be any misclassification happening, no misclassification at all. Okay. So in that case, like like we just need to maximize our margin or minimize our half of omega square or W square, such that this should hold true. Okay. Now how does this thing actually comes up, a separate idea, like need not get into the that stuff. But overall is in SVM, the class labels are not 1 0, they are considered as -1 or 1. So what we want is, we want whatever W transpose xi plus b, what it is telling and y, they should be of the same sign. Then only my stuff would be working out, my model would be working out. If they are of opposite sign, in that case it doesn't make sense, because how the decision is taken is W transpose xi plus b, we take the sign of this, whatever is the sign of this is considered as the class of my data point. So if it's positive, it's positive class, that means +1. If it's negative, it's considered -1. So you can just see, if I multiply it by yi, if it had been correctly classifying, I would always be getting it as greater than 1. Okay. Or something like overall idea is greater than 0 will be getting, or less than 0 if there is a misclassification taking place. And this one is actually to help us with respect to the geometrical, forgot that, geometrical margin. Yes, functional margin and geometrical margin, there are these two things. So this is just to account for that it shouldn't be just greater than 0, but there should be a proper distance between them. That's how we bring one detail in that can be found in the lectures. Okay, not required right now. Now within soft margin, what do we say? We say that okay, we are still optimizing for the same thing, but we allow some misclassification. We allow some data points to cross these hyperplanes, these gatekeepers which were built. Because earlier I said the gatekeepers would not allow any data point from this class to come here, data points from this class to come on this side. The hard margin never allows that, but for soft margin I'm saying that some points might come here, or maybe cross. That means one of the data point 2 3 or some data points of this class might be entering this area as well. It's possible, or in between these two as well. So that's possible. So wherever this gate is being crossed, then in that case all those points are also called support vectors. So in hard margin hard margin SVM, the support vectors are those points which lie on these hyperplanes, these two which I had been talking about. Okay, the two hyperplanes which we actually find out, and then the midline is always our hyperplane decision boundary. But for soft margin, whichever data point actually crosses these two gatekeepers from their corresponding class side. What do I mean is, so for an example, if this point was belonging, like if this was the class, if this point is coming here, crossed it, or maybe it crossed the other gate as well, in that case they also become the support vectors. Okay, so that's the overall idea. But within my cost function, we add this component as well, c times of summation of psi. Now, what is this xi telling me? This xi is nothing but this xi gives me the scale of uh, uh, what should I say? The penalty I'm getting because of my what should I say? Whenever my data point is crossing these hyperplane or the gatekeepers, whenever they are crossing it, we'll get some value of xi in that case. And capital C is the one which provides the penalty for misclassification. So you can see my xi value would keep on increasing the moment these data points, let's suppose there was a data point over here, just cross this, come on the line, crossing, cross the other gate as well. So it keeps on increasing. Okay, so that's the overall idea for the xi. That means it is telling me about the overall either misclassification or an issue we are running into, that we are allowing some of the misclassification or my boundaries to be breached, we are allowing that. Okay, and capital C actually controls that. So just think about this: if I'm increasing C to a very large value, in that case what I'm saying is each of the small xi value would be contributing a lot to my overall cost function. That means what I want is, we want no crossing of the gatekeepers, no crossing of the of the gatekeepers boundary, like these two hyperplane I was talking about. We don't want that. That means while increasing the capital C, I am actually making soft margin a hard margin. Okay, but if I am decreasing the C value, I am saying the misclassification is fine with me, like making capital C to be 0.0001. Think about this: even if there was a misclassification because of which I'll be getting high xi value, the contribution of that would be very less, so I'm allowing it. So that means soft margin actually allows for what? The misclassification. It actually helps in outlier treatment as well. So fine with it. So hard margin actually is something like this. Within soft margin, I can expand my margins a lot because I'm allowing some misclassification or the gatekeepers to be crossed as well. Okay, so that is our soft margin. Important points: only support vectors define the boundary, especially for the hard margin. But when it's soft SVM, in that case, support vectors are also the ones which actually cross the boundaries. Okay, margin maximization is the problem. By doing so, we are giving better generalization. SVM does not output probability. Larger C reduces the margin. So if I'm increasing the C, that means I'm allowing for lesser misclassification. While doing so, I might decrease my margin. Okay, it's possible. So it happens because if I'm moving from like I'm increasing C, so in that case I do not want any misclassification, I do not want any gatekeepers to be crossed. So that means what I'm doing is, there were some points lying over here, I'm decreasing it so that I can reduce it. So it reduces the margin, lowers the bias. The error for on the training might decrease, but overall might increase. Okay, hinge loss, this is the kind of loss function which we use in SVM, which we talked like initially as well. Then there is a kernel trick, very important kernel trick. So in linear regression we always have this polynomial regression kind of an idea, where we actually does feature transformation to go in higher dimension, where my my relationship of features might become linear with respect to my label or output variable. But do we really need to calculate my features in high dimension? Is the idea of kernel trick, in which we do not create my features, but that is something implicitly done and help us in solving without even getting to the higher dimension directly. So what I'm saying is, we use some kind of a kernel idea which actually transforms my feature into higher space, but they are never explicitly calculated, because if you know, polynomial features are explicitly calculated and then fed into the model. But in kernel trick, what do we do is we use a kernel which implicitly converts them to higher dimension. We are not saying that what exactly is going to be that higher dimension, okay, or we are not calculating them explicitly, but that kernel directly is being used for modeling purpose then further. So that means we are not making it to higher dimension directly, but that is something inherently which is happening. And when we know, like if something like this is possible, if we make it complex, if we go into the higher dimension space, we generalize better in general. Okay, we can reduce, we can understand the pattern much better, and that's the kernel trick over here. Different kernels, yeah. One more thing, the kernel idea is to tell you, like overall idea being used is that kernel is nothing but a kind of a dot product only, which tells the similarity between 2 points in higher dimension. Stuff like this only, simple. So linear kernel is nothing but a dot product polynomial. We add a C component and take the power of that, and then RBF is radial basis function, which is very much common to actually learn the complex decision boundary, decreasing my bias a lot. So yeah, these are the three important kernels. Like in general, X transpose X is something which matters. So if I can, if there is something which is being used in form of X transpose X, kernel can be used directly over there. Okay. The next is decision trees. So it's a non-parametric supervised learning method that predicts by learning simple decision rules. Okay, it uses recursive partitioning of feature space to give axis aligned decision boundaries. Okay, very good. So like KNN, decision trees also assume nothing about your data. That how does your data look like? They have no assumption. That's why it's non-parametric. And how does it actually like learn? For each of the feature, it tells that okay, if I'll be going for this particular feature, if this value is less than this, I might get something like this. If it's more than this, I might get something like this. So that's the idea. So in decision trees, your decision boundaries are never a line, a single line or a single curve. It is actually a lot of grid structure being created. So a vertical line, then maybe horizontal line, then something like this. So just to create, like, it shouldn't be like I'm doing kind of karate practice. So something like this is possible. So you might get, that's possible, you might get something like this. Okay, grid structure like this. So, and these are the decision boundaries which are always axis aligned. That means parallel to axis. You will never be having a tilted a line or tilted decision boundary. You will always be having parallel to your axis. If it's two dimensional, so all the decision boundaries would be parallel to x axis and y axis, overall giving you a closed rectangular structures. Okay, rectangular decision boundaries. Cool. So the idea is we'll be having all the data present in the root node, and then we split the data according to what can be the best split I can use, so that I can split them into two different set of data points, such that we, like, they are much better to classify whatever class we are trying to do. For an example, if I know that a simple example can be something like, uh, let's suppose it's winter time or not. Okay, so if I want to find out whether it's winter or not, there can be multiple things which you can consider. But if I know the ice cream sales, so if ice cream sales are too much, I know it's not winter, it's basically summer. But if it's too less, in that case, I'm much more sure that it's going to be what, winter. So simply one feature could tell me the overall split. There further can be other set of features which can help me better in splitting those data points further in order to get good kind of nodes or good kind of data points where I'm getting pure kind of nodes. What is pure kind of nodes? What do I mean by that is that I'm getting only one type of data points together, because ultimately idea is this only, that we want similar looking data type to be together. Okay, so we might get into that kind of detail, that okay, ultimately I should get pure kind of nodes. So we are creating a tree where we keep on splitting based on some of the features. Now how do I split? So there are a number of ways or number of mathematical formulas being used for that. Entropy, information gain, gain impurity, the formulas are also written over here. Entropy and gain impurity are nothing but they are kind of measure of impurity. So while splitting, what you want is you want your impurity to decrease as much as possible. You want to decrease your impurity. So that means because of the split, if you know the impurity is getting decreased, you'd like to go by that particular feature, because at any level, if I want to go to the other level, I have to split based on some feature. What should be that feature? It is very important for us. Okay, so now how do we determine that? Based on any three of these. So the first and third are just impurity. Second is more on uh, kind of opposite of impurity. So if I'm like, so second is actually talking about decrease in the impurity. So the same thing which we talked about for first and third, but just in opposite way. So wherever information gain is high, not the impurity is high, information gain is high, we would like to go by that. Now when I say information gain is high, that means wherever I was getting least impurity because of the feature, that would give me overall difference, because this is entropy. Okay, so if I take the difference, the information gain would be high if I had lesser entropy. So you can just chase the least impurity, least gain impurity, or highest information gain for a feature. The feature which gives it, you would like to go by that. What is the overall stopping criteria? When do you stop creating the further levels? So there are a number of things you can do that, based on which you have to decide maximum depth, how far you can go. Pure node, if in a node you have got all the data points belonging to one class only, you need not go further, because then you have understood that yeah, this is a pure kind of node, and any data point which would be coming over here would be belonging to this class only. Minimum samples per node, this is very important. See, so the idea for this one is that whenever we talk about this, we want at least a good number of sample in each node. I do not want one sample in a node, because in that case it's going to be very like it would vary a lot, because based on just one data point I cannot predict what should be the class. So I want good number of data points or samples within each node. So we can just fix a bar on what should be the minimum number of samples per node. If it decreases from that while splitting, we would not like to go for the split, even if the node was not pure. That means if, let's suppose, we had 3 belonging to class 1, 4 belonging to class 2, it's fine, because after splitting, if I'm getting, let's suppose, within one within left side, if I'm getting just one data point, we don't want that. We want to keep 3 versus 4 idea, where I would always be predicting that with 3 by 7 probability, the class is going to be class 1, and with probability 4 by 7, the class is going to be class 0 in that case. Okay, what are the okay, important features? Features doesn't mean the machine learning features, features of decision tree. So it is much more interpretable, because it actually go by the features only, like what exactly is the feature, which features you're picking. So it determines whichever feature is picked up on top are the most important features for us, because that actually split up very best. Okay, prone to overfitting. So if we keep going down and down and down, we might be overfitting, because what, so if I do not restrict the maximum depth or minimum samples per node, like the first and third, if I do not restrict on that, I might get in each node just one data point at last, which would be prone to overfitting because I overlearned everything. Okay, I learned the noise as well. So that's the problem with decision trees. They are very much prone to overfitting. Unstable to small changes. So if the data changes a bit, yes, because we are just going by the scale of our features. So yeah, that's a problem. Can handle nonlinear boundaries. So I just mentioned it can actually help us. So for an example, if my some of the data points were lying in, let's suppose over here we had all these, over here we had crosses, over here we had this. So this is kind of thing possible with decision trees easily. Okay, but we cannot really do this with every other algorithm. Okay, so it can handle non-linear boundaries. No feature scaling needed because there is no distance calculated. It is splitting on the scale, but we are never calculating the distance, so hence feature scaling is not required. Overfitting tree goes until very every leaf is pure, often leading to high variance, you know that. So that's where pruning actually comes into the picture, and pruning is based on this idea: minimum samples per node, or we can just specify what is the information gain, minimum information gain I want for each split. All that stuff can be used for pruning. Okay, now this is a time space complexity table over here which you can use. uh, One important thing, so like over here it's mentioned what NDT actually refers to. Okay, so you can use this, but remember one thing which is very important. You basic sorry, so for not every algorithm you might be able to understand it right now, because that needs a detailed discussion around that, but can still be understand. Okay, so for an example I can help you. Wherever you can see d cube, that is more with respect to the matrix eigenvectors calculation or matrix inversion. So wherever you are seeing d3, that means we are actually talking about d cube. That means we are talking about there is some matrix inversion taking place. Very important. Capital T, so is actually referring to the stochastic gradient descent or batch gradient, basically the number of iteration. Capital T is actually talking about that. M, number of support vectors. So you know in linear, uh, so over here it would not really matter much, but for kernel it actually matters a lot, that what is going to be my number of support vectors. And yes, it's not just the train time, it inference time plus space as well. So you can just go by that idea as well, what is being used for decision tree. You know, we have in general like, um, we need to sort our features if it's continuous, and then we have to figure out what should be the value at which I'll split into left or right. So there is always this sorting for each of the feature which takes place. So n log n for each of the d, so d into n log n, and then there is some depth until what we will be going. So all that stuff, so you can see, you can understand. If you know this already, you will be able to recall, but if not, you can skip, and or you can just focus on some of these. For an example, you should know these at least. mm, Ridge is also on the same side only. mm, you can skip others. Yeah, you can skip others until naive base, it's fine. Okay, but remember, if you want to have this discussion, we can always do, because that needs a little more time to understand. That's why I'm not devoting much time. But if you can recall, if you're good at, like, if you can cram it right now in lesser time, in that case it's fine. So next comes up our bias variance trade-off. So this is very fundamental and used very often in machine learning to understand the performance or generalization error. So what is this? We overall we always want our generalization error to be less. Okay. Now, while doing so, while modeling, we actually look for several things. There will be training data, there will be testing data. We will be getting some test error, train error, and then there is some irreducible error as well. So, like, we classify each of these errors as something important, and then talks about how we can decrease each of these, or whether it's really possible to decrease each of these or not. Okay, so yeah, So the overall error is expected value of y minus fx cap. So fx cap is not just the model which we predicted. Fx cap is a, a mean model or an average model or expected model. So I'll be having, for an example, if I'm saying I'm using linear regression model, so I might get a number of linear regression model. So overall, if I use the average model on top of that, then what would be the expected value of my error is what I'm talking about. Okay, so that is going to be bias square, which is nothing but error from the wrong assumptions, variance plus noise. Now, what is this bias square? So there is this further detail is also written. You can just read that too, but I'll explain. Bias is much more related to the data. Sorry, much more related to the model. So if the model is complex, I might reduce the error, but what might be happening is I am overlearning. So bias is something which can we can easily decrease by making my model complex, by bringing complex feature transformations. Okay, we can always decrease our bias. So bias is always intrinsic to the model capability, model complexity. If the model is complex, bias would decrease. If model is not, in that case bias would uh, remain high. So that means error from wrong assumptions. Why? Because my model, the choice of model actually is determined from what actually I assumed about the overall assumption I had about the data. Okay, depending upon that only we actually create our model. So that is my bias. Now, what is variance? Variance is much more related to sensitivity to data. For an example, uh, I created the model, but what happened was my training data was different from my test data. So in that case, I might decrease my training error, but my test error would increase because the behavior of my test data was itself different. So the idea is, what is my variance or the error because of variance? That is nothing but telling that what assumption I had with respect to the data, how it looks like, is wrong. Okay, so you can see both the things here. Also it's assumption, here also the assumption would come, but here assumption would be more with respect to my modeling perspective. Over here my assumption would be with respect to my data perspective. So that means the data which I am using right now, if it's not representative of true data, my variance would always be high. Okay, and if I understand, okay, whatever training data I'm having, if I scenes, and if based on that, if I think of what can be my best model looking like, and if I try focusing on decreasing most of my error, I might make my model complex, or complex models can be used, thereby decreasing the bias. But if it's not representative of true data, my variance would increase. What is the third component? Noise. There is always this component which we cannot really get away with: irreducible error. We cannot decrease that anyhow. Okay, so that's the component, three components: bias, variance, and noise. Cool. Again, bias, variance of all the ML algorithms we talked about. So if I'm saying linear regression, the bias and variance is moderate. So see, bias would be very less if I know the data was linear. But if it's not linear, in that case, I might increase my bias, and hence variance would overall decrease if the data was not linear. So that's why they are kept same, moderate, moderate. But in general, if I assume it to be linear, my bias would be lesser, my variance would be higher. Okay, ridge. So it's a regularization technique. My variance would decrease, my bias would increase. Lasso, logistic. Logistic is similar to the linear regression. KNN we talked about. Naive Bayes, yes. So what actually happens is, over here as well, so we actually go by the probabilistic aspect. So with respect to that, definitely variance would decrease. We are not just thinking about that, okay, what I'm actually able to see. It's much more, the prior actually helps us in, like, getting to understand overall data as well. It's not just each of the data point I'm just referring to. Okay, so there variance decreases, bias increases. LDA, the same kind of an idea we are having again. SVM, yeah, decision tree. So this is, so wherever we have complex modeling, you can see we'll be having low bias, but my variance would increase. You can see, and decision tree we just talked about that it is much more prone to overfitting, so very high for the decision tree. Cool. So that was all about the bias and variance. Next comes up our cross validation. So cross validation is a recent technique used to evaluate how, okay. So what is cross validation? So we were actually going by train error, test error, but we actually want to understand the overall generalization error before even exposing the test data. Before even giving the test data to evaluate, we would like to see how does it overall generalize. Now for that thing, from the training itself, I have to keep some data aside to validate that, and that's how we actually bring the cross validation. So there are prominently two main methods. One is k-fold, the other is leave one out cross validation. In k-fold, we actually create, for an example, if you had like 100 data points and you want to do a k-fold cross validation using, let's suppose, 10 fold, so you'll be dividing your entire training data set into 10 parts, such that every time you'll be picking up 9 folds to train and 1 fold to test, and that one which you are using for testing would become your which will become your it will become your validation data. Okay, so we have divided it into k folds. Now the k minus 1 folds are being used for training, one is being used for testing purpose over there, or validation over here. I should like testing, in general testing, but it's not the test data, it's the validation data. Test data is still kept outside. Okay, and then we can calculate everything, like all the errors, we train it, and the overall average performance is being seen, because in that case we can see different validation data points, which will help us understand if the overall data changes, what can be my overall generalization error. Okay, leave one out. So within this one, so this is more specific to when we have least amount of data, because then in that case we cannot create, let's suppose in one fold we cannot keep 100 data points or 1,000 data points, not possible. So in leave one out cross validation is for those when we have lesser amount of data available, in which the k value is actually becoming n. That means the number of data points we use to train is actually n minus 1 data points, if n is the training size, and 1 is only being used for validating, testing purpose there. Okay, so that's the idea in leave one out cross validation. Yeah, there is one more, which is, yeah, stratified, is over here. Stratified k fold. What is that? So we want to create these folds, but there may be the class imbalance which is possible. For an example, in my entire data set, I'm having 80% of positive class, 20% of negative class. Now while creating the folds, I might get all the 20% in just one fold, rest in the 80%. So that would be a problematic situation. We don't want that. We always want my training data, or whatever data I'm using for training my model, to be representative of true data. So in that case, I want that proportion to hold in each of the fold. That means if I'm having 10 data points in a fold, in that case 8 out of 10 I want to belong to the majority class, 2 out of 10 to belong to the minority class. That means 80-20 ratios should always be followed for each of the fold as well. So that's kind of something like stratified k-fold cross validation. Then we get okay, so you can just read through this, in general, in leave one out cross validation, your training data would always be highly overlapping, so models are highly correlated, so you would get lower bias, but your variance would be very high, because you have just one data point which is actually different from the rest. Okay, yeah, bias. So as I said about this, so as k increases, the bias of the error estimate actually decreases. Overall, it decreases because you got more data, you learned well, because the training set get closer to the full data set, but the computational cost increases. Choose the model with the lowest CV error. So you generally choose that model which had the lowest cross validation error. Cross validation error approximates the test error. It does not improve the model accuracy, but it is being used to pick up the best model or best set of hyperparameters. Okay, so that was about the cross validation. Then we get into the feed forward neural network, or basically the deep learning idea, neural networks. So in general, feed forward neural network is nothing but in which the information flow from one end to the other end. Okay, like yeah, feed forward, just ongoing, one direction to sorry, one end to other end. If information flows, that's our feed forward neural network. What is the MLP? Machine Not machine learning, multi-layer perceptron is just one class of special class of feed forward neural network, which actually uses this kind of idea. We will be having input layer, hidden layer, and then output layer, non-linear activation functions. Okay, and point to be noted, feed forward neural network are special type. Like there is a further categorization, special type of neural network which do not have any cycles within it, because you'll find it always flow from in one direction only. There is no cycle that okay, this node is again connected back to this one. Okay, because a simple example can be RNN, which is not simply a feed forward neural network. We have the loops as well, the feedback loops kind of thing. Wherever there is a feedback loop, those are not purely like a feed forward neural networks, but they are neural networks. Okay, multi-layer perceptron, we have input layer, hidden layer, output layer, and some non-linear activation functions are there. Why do we bring non-linear activation functions? Because if we do not bring them, it is nothing but a bigger linear regression model. That's the first thing which we learn generally. Non-linear activation functions are to learn the non-linear part within my data, because if I keep it linear, in that case it's the linear regression as I mentioned. So it would always be some linear transformation happening and then some non-linear transformation happening with the help of activation functions, and then we stack all these layers one after other to learn more and more. Okay, so key activation function, you can see sigmoid, tan h, tan hyperbolic, relu, leaky relu. You might not need right now, but just for the information, you can use softmax for multi-class classification problem. Okay, if you want to classify like out of 3 class, something like that. Okay, there is the range provided, the category sorry, characteristics is also provided. So yeah. Okay, so how does neural networks train? So they train with the help of back propagation. Back propagation is nothing but the advantage or an application of our chain rule only, because you can see like in the previous one only, over here we had one linear function, non-linear, we'll get some linear, non-linear. So that's how we stack all the layers in neural networks. Now, overall, the final output is nothing but function of function of function of function of function of this initial input. So there is a lot of function, some non-linear, some linear. Now you want to understand how you should learn the weights, the W's over here. How do you learn that? Now for that, it's similar to your linear regression part, where you actually take the derivative and you like how does gradient descent work. So it's just back propagation is nothing but gradient descent only. So for the updates with respect to weight, weight is equal to weight minus learning rate into your what was your overall gradient of error with respect to this particular weight. So you want all that stuff. Now, how do you calculate? So, how do you calculate the gradient with respect to this W? Because there are multiple layers. Then, with respect to this W, for the last one, it might be very simple, similar to your simple linear regression, because that was the last weight. So, you can calculate the error easily. And then, with respect to this W, what was the overall gradient you might get? But as you go back, how do you calculate that? You use the chain rule, because each of these function was function of previous function of previous layer, which was a different function. So use a kind of a chain rule, f of g of h of something like this. How do you take a derivative there? F dash into g dash into h dash, all that stuff. So that is the back propagation, nothing different. Back propagation is algorithm used to calculate the gradient of the loss function with respect to the weight. It uses chain rule from calculus. Forward pass, simply compute the output, and the loss error. Backward pass, you calculate all the gradients to update the weights. Update rule, we know. I just talked about this. Now there is an important point. Universal approximation theorem. What exactly is this particular theorem about? So this tells us a feed. Okay, so overall idea is universal approximation theorem says that a neural network can approximate any function, any non-linear function. Okay, it can do very easily with just one single layer, hidden layer, and a finite number of neurons. It just need to be, we have to have a good number of neurons in just one single hidden layer. So that means this actually shows the power of neural network. So if we stack a number of things, in that case it would be doing good. Deep neural network, if I'm talking about. Okay, so that's the, sorry, universal approximation theorem, that we can approximate any function. Now there are two problems very famous in neural networks: vanishing gradient, exploding gradient. Vanishing is when my gradients becoming smaller and smaller. Why it is a problem? Because my gradient flows from your near output layer to your near input layer. So it's like if your, this was your input layer, this was your output layer, your information flowed like this, your error uh, or your gradients in back propagation would flow from this side to this side. Okay, now if in between your gradients become so small, if it becomes zero, there would be no learning taking place at initial set of layers. So how to handle that if your gradient is becoming zero? So it generally happens because of why, like when you have deep neural network, if you have a number of layers over, like extra layers, it would keep on multiplying, making it zero. So in that case, how you can avoid it by simply bringing some like better uh, better activation functions. So if you're using sigmoid or tanh, which actually keeps everything between like -1 to 1 or 0 to 1, and while multiplying everything, it would tend to become smaller and smaller. You should use better activation function like relu over there. Okay, so relu can solve a lot of problem over there in vanishing gradient. What is the exploding gradient problem? um, so it happens again if by any chance, if your gradients are much bigger, and if you have a number of layers, in that case, while multiplying gradients with each other, it might explode, it might become very large. Now you want to keep them bounded. There you use gradient clipping, that you actually define a range for gradient, and you would say that it should not go beyond that. If it goes, you clip them up, you keep them those as the gradient values. Okay, bias and variance. If the neural network is shallow, the bias can be higher, variance can be lower. But if it's deep neural network, we tend to get lower bias because it even learns the noise. Variance becomes higher in that case. So that was all around the feed forward neural networks. Now next is our clustering, and we are getting into the what should I say, our unsupervised learning now. So clustering idea is to cluster the those data points which have the same behavior, same characteristics, same properties together. That is the idea. Now in our syllabus there exist two types of method. One is partitioning method, and the other is basically what is it, hierarchical method. Okay, we create the hierarchy tree like structure over there. Partition, just simply partition within a non-overlapping cluster. So for this one we have two methods in our syllabus: k-means and k-medoids. How does k-means work? So k-means means, that means we will be using mean over here as the centroid of the cluster. Okay, so what we want is we will always be having so what would be mean telling me, or what would be centroid telling me? Centroid would be telling me a kind of a central tendency of the cluster. So it's like something like this. I would like to see a leader of a cluster, and when I say leader would be representing the all the cluster data points. Okay, so what do we want? We uses a leader to actually fight among themselves to find out what is their true sense of, what should I say, public, or candidate around them, or who can follow them. So in general, I'm just giving you the idea. So k means tell me, so initially you will always be having that how many clusters do I need? I need 5 clusters, 4 clusters, 3 clusters, depending upon that. It's like you are going to conduct a voting thing. So you have already known that that you would like to see 3 leaders or 4 leaders out there, and then you let them influence the public. Okay, whichever leader finds the most of, what should I say, identical behavior with respect to the people around them, they'll say that okay, he's more like us. They then, in that case, that would become leader for that particular cluster. Okay, and within that case, then there is a further discussion going on. They give rise to another candidate which becomes their leader. So leaders keep changing, but overall the number of cluster remains same. So the initial idea is as if you actually give that initial what should I say, ignite a fire to say there should be 3 leaders, and then you're randomly sending 3 people to actually try out and get me the best candidate. They talk among themselves what might happen, what should be the scenario. Like, I'm just giving you in general example, but in our what should I say, in machine learning, how does it happen? That we have some randomly initialized centroid, and then those centroid would be actually looking at what is the distance from each of the other data points we are having. Now, whichever would be having minimal distance, because for an example, if I'm having 3 candidates, 3 cluster I want, so I'll be having 3 data points. Now I would like to assign each of the data points to one of these data points only, one of these centers only, because I want 3 clusters. So it's just remember that whenever I'm saying 3 data points initially, the k means I'm talking about, consider them to be a kind of a candidate or representative of a cluster. So if I'm saying I will calculate the distance of all the data points from the first centroid, second centroid, third centroid. Now for whichever centroid, for any data point, the distance would be minimum, that particular data point would belong to that centroid. Now we assign that, and that's how we create a population for each of the centroid. After we complete that, what happens is we calculate what is the overall what should I say, central tendency. Now what is the overall centroid of the data points which belong to this cluster? So there would be a new centroid coming up for each of these 3 clusters. Now again we try to calculate that. Okay, that whether the cluster I'm having right now is perfect or not, or there can be still some changes, and it happens. We have seen it in RIC batch. You can just check out that we have solved some good question. So we again calculate the distance of all the data points, even if it belongs to our own cluster or some others. We actually calculate all the distances. Now again, for whichever centroid any data point would be having least distance, that data point would go to again the cluster of that centroid in that case. So this keeps on going until it the centroid does not change, or the membership of the data points does not change. Okay, it's very fast, efficient, but sensitive to outliers because we are using the distance metric over here. And in that case, it becomes sensitive. Plus initialization. If I am initializing very bad centroids initially, in that case, we would suffer. So the like the better thing we can do there is k-means, which actually try to pick up the data point, sorry, centroid from the existing data points, while keeping the idea in mind that okay, they should be far from each other as well. So two important improvements because of k-means. They actually comes up from the data points, okay, because in k-means, a simple k-means, the centroid need not be from data points. In k-means plus plus, they would be from your data points, plus they would be scattered in such a way that they would be at a maximum distance from each other. So somewhere they're kind of representing a true distance from each other. Okay, so yeah, that's the kind of k-means plus plus which actually fasten this k-means clustering. Now next is k-medoids. Now what is k-medoid? So as we talked about, distance is always prone to outlier issue. So in that case, if I do not calculate the distance, in mean we have to calculate that and all that. How to do better? So in that case, we can always use median for that. So instead of centroid, what if I use the median to calculate my centroid candidate? So we use instead of mean simple standard calculation, we use the medoid, which is just like what should I say, similar to the centroid thing, but using the median, we calculate medoid, and then we use the same kind of thing which we had been doing for our this thing. Our k means. Okay, so important thing is that k medoid is much more robust to outliers than k means, because medoid is an actual data point you'll always be getting, not any not any point from from the cluster of data points. Okay, so it might be possible something like this, that if I had these this was the cluster, circle is a cluster, and these are the data points. Now in that case, my k means might give this as the centroid, or something which is not even a data point as the centroid. It might give this as the centroid possibly, but k medoid would definitely be giving in that case this kind of a data point to be medoid, because it will always be coming from the existing data point, not creating any like central tendency where there is no data point existing. Okay, now the second thing, second way of clustering is hierarchical clustering. We create tree-like structures called dendrograms over here. So there are mainly two approaches over here. And the first one is most common, bottom up. We actually start from the bottom. We start from by assuming that if we have n data points, we have n clusters, and we keep merging the clusters based on their similarity until we get to reach just one cluster. Okay, so that's how we create the data, like that's how we create this dendrogram or clustering. That's how it takes place. Now as I mentioned, there is this merging of clusters takes place that actually considers again some distance metric. Now, because higher the distance, lesser the similarity, more the similarity, lesser the distance. So now it matters a lot that how do I define that distance metric. On the basis of that only, there are different variants which actually comes up. So overall, bottom up is agglomerative hierarchical clustering. Okay, most common as I mentioned. The other is top down, which is division, in which we start from one cluster and then we recursively split it, which is not really common for us. It's generally agglomerative, which is and it is also the part of our syllabus. So with respect to agglomerative only, so we are going to talk about this. So there is this linkage metric which actually define that how do we merge the clusters. Okay, single linkage. So if we had two cluster, we would like to see minimum distance between any 2 points. So it's like if I have these 2 points, this point, like you can see, this is the end point with respect to like the configuration I'm creating, and this one. So these are at the farthest distance from each other. The closest one are represented by my thumb. I hope you can see this. Okay, so this will give me the distance for my cluster. Now, wherever for the closest data points within the cluster, I'll be having minimum distance. I would merge those. This is single linkage. What is complete linkage? So as I draw, like when I was showing this, my this smallest finger, last finger, would be telling me, like if I will be using distance of these two, that would be giving me a complete linkage. That means I would like to see the maximum distance between any 2 points, between two clusters. That would give me the complete linkage. Now I would like to see which has the minimum maximum distance while merging. So for example, between these two I'm getting this, I'll be getting these two clusters, some more. So for each of these two, I'll be seeing that what exactly is the like what are the clusters I can club based on this distance. Average linkage would actually be calculating the average distance between all pair of data points. If I had m data points here, n data points here, so overall how many distance needs to be calculated? M cross n. M into n number of data distances would be calculated. Their average would be representing how uh, similar these two clusters are. Now after that, there is this Ward's method, which actually minimizes the increases in total within cluster variance after merging. So it uses the variance idea, not really important for the examination point of view, but there's something like this which actually exists. Okay. Uh, so yeah, this was overall with respect to the linkage. I hope that's clear. Next is our dimensionality reduction. Yeah. Now we are moving towards the end of this session only. So dimensionality reduction. PCA, unsupervised dimensionality prediction, is like PCA only. How do we actually do that? So first idea is in PCA, like when PCA is happening, or when PCA is basically applicable when the data seems to be multicollinear, or the data seems to be non-orthogonal, the data seems to be non-independent. Okay, something like this. So what do I mean by this is, so you by default know that if I'm talking about my features, it's possible that uh, like there can be something like one can influence the other. For an example, if I'm having three features, let's say height, weight, BMI, I know height and weight are completely independent of each other. Okay, completely. But like in general, not in general. In general, it's not completely unrelated, because if somebody is having high height, more height would be there. In that case, more weight is also possible. It would tend to have more weight in that case. So bad example. Uh, age and oh yeah, age and weight is also. Yeah, color. Okay, so skin color and weight, something like this. So these two are completely unrelated to each other, completely unrelated information. In this case, what happens is, this can be like each of these two features can be very important rather than if I bring height and weight, because somewhere one can represent the other one. So what we want ideally in like in machine learning is, we want to get completely unrelated set of features which can combine, when combined, can give or like determine my label very easily. Because if I have the what should I say, uh, correlated or related variables or features, in that case there are 2 3 problems coming up. One is multicollinearity, like like there would be a problem because in interpretation itself. One would be curse of dimensionality, why to increase so much of like features, why to have such number of features, we should decrease them. So all that stuff comes into the picture. So the idea is to keep independent feature, unrelated feature, and less number of features. That is the idea. And that's where the PCA comes into the picture. We want new orthogonal axis. By orthogonal we actually mean that they would be completely unrelated. Kind of unrelated doesn't mean unrelated to the label, but unrelated to each other. For an example, the perpendicular axes. Okay, because you cannot determine change in this, what would be the change in y. But if I am having a line like this, I know, if I know, like if it's like this, a change in this can bring some change in this, I know what would be that change. So we want that kind of a thing. We want completely orthogonal axis, and that would be derived from existing features. So what we do is, we actually transform the same feature in such a way in the same space. If we have 20 dimensions earlier, we'll shift it to 20 dimension in such a way such that I'll be getting orthogonal directions, but there also we are ordering it by the importance, that how much of my variance I'm able to capture. We order it by that particular thing. Okay, so we find out the orthogonal excesses, which are nothing but linear combination of original features. That means if 20 was the initial set of features, we'll be getting 20 orthogonal excesses right now. But we would like to use those in which my data varies most. If in one of the dimension my data is not really varying, why to keep that particular feature? So we actually decrease the we order my orthogonal excess or principal components with respect to decreasing amount of variance, and then we pick top k. So if I wanted 3 features, 5 features, 6 features only, then we just consider that many initial number of principal components or orthogonal excesses, and that would become not that would become those would be used to determine my actual features by simply projection further. Okay, so you can see over here that's being like written the same thing. The process is also that, like, first of all we need to standardize, because for some of the features my scale can vary a lot. Okay, so need to consider that thing in mind. Compute the covariance metric, calculate the eigenvectors and eigenvalues, sort eigenvalues in descending order, largest eigenvalue correspond to the first principal component, project original data onto these k eigenvectors. So whatever was our data, we will project onto this, and that's how we get our new set of features which is required for us. Okay, so this is my overall PCA principal component analysis, which actually just compress the data, not with respect to any it doesn't have any supervision, but it just considers the idea of what idea of variance, and it uses the linear projections for that. So no non linearity thing is being considered over here. Now last set of points we are getting into for this. K-means is a greedy algorithm and can get stuck in local optima. Always remember. Okay, that's where we need a different kind of initialization. Dendrograms allows you to choose k after the algorithms runs by cutting the tree at a certain height. So if you can see that what exactly your clusters look like, because you actually starts from as many cluster as many data points you had, and keep building up lesser and lesser cluster using the dendrogram, you can always determine how many clusters you want based on the nature of clusters you got by now, and then you keep to move ahead. Sorry, you can cut the tree to move ahead, and whatever clusters you're having, that would become your overall number of clusters right now. PCA is not a feature selection tool, but rather a feature extraction or feature transformation tool. Remember that. If you have highly correlated features, PCA is an excellent way to handle multicollinearity before running a regression. Another important point, if your features were already orthogonal to each other or unrelated, then applying PCA does not really help. You would get the same set of features again. And if the variance was also same across all, in that case also, like, it would not really make sense. You would just lose information by keeping lesser number of features in that case, if the variance was also same across all the dimension. So that was all about machine learning short notes. I hope you could enjoy entire machine learning in short within I guess 1.75 hours. That was all. Thank you guys for attending this session. I hope you'll definitely get some benefit out of it. Uh, See you guys. I would not take up much more time over here. Uh, you might need to try other short notes as well for other subjects. So yeah, all the best, and thank you for watching this video. Bye bye.